All right, looking back again, the idea of enantiomers and diastereomers, we're going to see that enantiomers are those non-superimposable mirror images. Diastereomers are the stereoisomers that are not superimposable and not mirror images. We saw this was the first idea of this was the cis and trans stereoisomers exist here, but there's more, right? So cis and trans stereoisomers, looking at the double bonds, right? Those ideas, those stereoisomers are specifically diastereomers. They're not mirror images. There's no way you could rotate them or find out that they're mirror images. They are non-superimposable though, right? Their connectivity is different, is the same, but their orientation of those connections is different. Diastereomers have different physical properties. Cis-butene is more reactive than trans-butene. Trans-butene is more stable because those big groups are on opposite sides of each other. Now, when we get big cyclohexane groups, when we get lots of substituents on molecules, when we get more than one chiral center, that's where we get the diastereomer, and we're going to practice this a lot. But what's really important to note is that when you have 3 substituents on a cyclohexane, and all 3 of those carbons in cyclohexane are chiral, there are 8 possible stereoisomers. Holy cow. Notice the enantiomers, right? These are enantiomers, and so are these ones, where all 3 chiral centers are opposites. We could find the mirror images of these if we drew them all out in the chair conformations. Go for it if you really want to. But you split up and you go to a different pair, that's a diastereomer. That's a diastereomer, that's a diastereomer, that's a diastereomer, that's a diastereomer. Diastereomers are all the other relationships that we have. What's really important to note is that there are only 2 molecules that can be a pair of enantiomers. If you have more than one chiral center, 2 chiral centers or more, right? If the chiral centers are exactly opposite, that is the enantiomer. If one stays the same and one is different, that's a diastereomer. We can think of this as a family when there are 4 pairs of twins, right? A total of 8 kids. Each kid has 7 siblings, where one of them is their twin and the other 6 are their diastereomers. It's a scary thought to think about, but that's a, good one, good one. Now here's the rule. For the number of possible stereoisomers to be determined, we look at the number of chiral centers, 2 to the n being the number of chiral centers. So if you have 1 chiral center, 2 to the 1 is 2. There are 2 possible stereoisomers. They're going to be enantiomers. There's no diastereomers. That's the simplest way. But if you have 2 chiral centers, 2 to the 2 is 4. You're going to have 2 pairs of twins. You're going to have 2 pairs of enantiomers, and everybody else will be the diastereomer. Here's cholesterol. How many? 1, 2, 3, 4, 5, 6, 7, 8. Yikes. Yeah, there are a lot of possibilities for stereoisomers. And guess what? Cholesterol is the one that works in our body. So crazy. Any compound with 1 chiral center will be a chiral compound. With more than 1 chiral compound, it may or may not be chiral. Here's where I was hinting towards a new word. And I just want to present these guys again from the very beginning of our lecture. This versus this. Now we can categorize these. Are these enantiomers or are they diastereomers? Well, notice that they have both the wedge methyl on the top and a dash on the 1 and a wedge on the 2nd for the bottom carbon. They would be diastereomers, but let's look at this compound a little bit more closely. The trans isomer is chiral. It's optically active. This cis isomer is achiral. Not because it's specifically cis, but it actually has a plane of symmetry in it. What's really important to understand is when we have a plane of symmetry, I wanted to draw it here in these projections so you can see it. You can also see it in the skeletal structure. That plane of symmetry, I call this the taco. Think about folding it in half like a taco shell. That plane of symmetry creates an achiral molecule. Think about this trans. This trans guide, there is no symmetry. And that's because one of the methyls is wedged and one of them is dashed. Now, the cis isomer will have a plane of symmetry when the substituents are identical and cis, right? So this with two methyls is symmetry. Same thing here. Cis, two identical groups. Where's the symmetry? Right there. We gotta practice finding this symmetry because that means that this compound is achiral. Same with the other one. The 1,2 dimethyl is the same as, is achiral, and so is the 1,3 dimethyl when they're cis. Molecules with an even number of chiral centers that have a plane of symmetry are called meso compounds. Another way to test if it's a meso compound is to see if it's identical to its mirror image. So let's bring up that cis 1,2 dimethyl again, right? We said it had a plane of symmetry, right? There are an even number of chiral centers. Now, let's imagine drawing the mirror image or drawing the enantiomer, right? I'm going to draw the mirror image. And then what I really want to do here is one of the beauties of the iPad. I'm just going to rotate this and look, it's superimposable. The mirror image should be the enantiomer, but these are not enantiomers. They are identical. That is truly what a meso compound means. Be very careful with these. We're going to practice with all the planes of symmetry and being able to do that. But if you have an iPad or if you're just writing this on a piece of paper, cut this out. Do some crafts, right? See that being able to rotate. Again, rotating the molecule like this, just spinning around kind of like a lazy Susan if you are vintage like I am. You know what that is. That ability is really important. Drawing a molecule or having a molecule kit is great. Drawing it, cutting it out, rotating, flipping, doing all sorts of things so that you manipulate the structure is extremely important. But if a compound has a plane of symmetry, it's achiral. That's the main take-home message here. That means it is not chiral, not optically active, does not have an enantiomer. Its enantiomer is itself. So therefore, it's not an enantiomer, it's identical. Now, be very careful. We will avoid a lot of reflectional symmetry, but notice that through this inversion point, we can kind of see the idea of symmetry. This compound is an inversion symmetry, and so therefore this compound is achiral as well. The molecule does look like it has two chiral centers and no plane of symmetry, but it's still achiral because of inversion. Overall, the presence or absence of rotational symmetry is irrelevant to chiral. Rotational symmetry, right, being able to rotate things or flip things, What really is important is having a plane of symmetry within the molecule. That makes it a meso compound and therefore achiral. The only exception for the lack of plane of symmetry is the inversion center. And that's the only one I expect you to note. Okay, here's a couple other options for a meso compound. When we look at these meso compounds, what's important to note is where is the plane of symmetry and can we visualize it? And notice things coming off are identical, right? It's kind of like having its own personal little mirror in there. Even this one right here doesn't have to be cyclic. Think of the taco. I relate a lot of things to food. Sorry. A meso compound also will have less than the predicted number of stereoisomers. Remember, because if you were to think about drawing all possible stereoisomers, the enantiomer is not different. These are equal to each other. So this is one of the options, right, for 2 to the n. That is not an enantiomer. These are identical. So usually meso compounds also have one less enantiomer or stereoisomer, excuse me, than based off of the 2n formula. Oh, chirality without chiral centers. We're going to talk about allenes mainly in class. Allenes are compounds that possess 2 adjacent double bonds. They may or may not be chiral depending on the substituents. So notice here, this carbon is sp hybridized. These two are sp2. Awesome. Okay. And the reason why the R groups are either in plane or wedged and dashed is because of the pi bonds. Now, remember that sp center has to have a pi bond on one X, Y, or Z, and the other pi bond has to be the opposite way, right? Perpendicular. And so these R groups are perpendicular to each other on opposite sides, right? So be very careful with allenes. The 2 groups on each end of the allene, if they are different, then the compound will be chiral. So if these 2 are different and these 2 are different, chiral. So quick example of allenes. If you want to draw them in a skeletal structure, this one would be achiral, because on one side we have identical groups, right? Still an allene, just achiral. What about this one? Chiral. Nice. No R-ness denotions, no any way of identifying. You just can identify chiral versus achiral. The chiral one that I drew on the right-hand side, the ethyl is different than the methyl, and the methyl is different from the hydrogen. So that's why there's different groups there. Excellent. Now, I hinted toward this at the very beginning of this chapter. For some molecules, cis and trans for a carbon-carbon double bond is inappropriate. It doesn't work because cis and trans is only if you have one hydrogen on each carbon of the carbon-carbon double bond. You have to have at least one hydrogen, well, only one hydrogen on each of the carbon-carbon double bonds. If you do not have 2 hydrogens in the molecule, one on each side, then you can't use cis and trans. What you do have to use is the E and Z denotion. And that notation was developed around the same time as R&S, but it's from a German scientist, and so E and Z actually has a purpose. We'll get there in just a second. So what we're going to do is look at these 2 compounds. These are diastereomers because they are non-superimposable, non-mirror images, right? So what we can do is we can start to say, well, how would we actually name this? Which ones would be E, and which one would be Z. We can't use cis and trans. We don't know what's on the same side or what's on opposite sides. Here's the process. Prioritize the groups on either side of the double bond. So smack dab, let's just draw a dividing line, and we'll say, who's higher priority? The ethyl, the carbon, let's call it carbon specifically, carbon or fluorine. Fluorine is highlighted red there because fluorine gets priority over carbon because of atomic number. Isn't it nice when everyone works together and does the same prioritization? Atomic number. Now, when we look on the opposite side, we have hydrogen versus nitrogen. Nitrogen is higher atomic number, so it gets priority. I usually put a little star next to these guys. And then I erase my dividing line and I say, awesome. I have my highest priorities on either side of the double bond. Now, once you have your highest priorities, then draw the line the other way, just like we did for cis and trans. And say, are the groups on the same side or are they on opposite sides? If they're on the same side, Z stands for zusammen, which means together. E stands for entgegen, which means opposite, German. So Lauren's famous German accent. If I ask you about the compounds and you say, Sie are on the same side, Sie on the same side. Z is German accent where, yeah, okay, cool. Moving on. E is just opposite side. If you remember Z, same side, then you'll remember Z is for together. And so we look at this first one where F and N are on the same side of that double bond. There is the Z. And where F and N are on opposite sides of that double bond, that's E. Nice. Let's just practice one more. I'll put this one in a ring structure. Okay, first thing that you do, draw a line separating the two sides. I'm going to go ahead and put in the hydrogen. I like to make sure I can see all of the things on each side of the double bond. And then I'm going to say on this top side, on this carbon right here, who's higher in priority, carbon or hydrogen? Carbon has the higher atomic number. Wonderful. Then I'm going to switch to the bottom, change color. On this carbon on the bottom, carbon or oxygen? Well, oxygen has the higher atomic number. Excellent. Now switch and draw a line so that you can see through the plane of the double bond. And are Z on Z same side? No, so it's E. Excellent. Thank you very much.